Hi, I'm Jill Boyce. I'm going to talk to you today about the MPEG Immersive Video or MIV standard. The MIV standard is under development by MPEG, and its goal is to enable viewing of immersive volumetric video content with 6 degrees of freedom for the viewer. The video is showing here it's illustrating 6 degrees of freedom. On the top row are the 3 degree of freedom associated with like 360 video, where the orientation of the viewer can change. So yaw, pitch, and roll, you can move your head in different directions, but yet you're staying in a particular position. Going from 3 degree of freedoms to 6 degree of freedoms is shown on the bottom, where we have 3 more dimensions of freedom, which is moving around XYZ position in space. So together, the 6 degree of freedom allows the viewer a lot of control over where they see a scene from. So immersive content can be consumed using a wide variety of devices. But the whole idea is that the viewer should feel immersed within a remote 3D scene. It could either be a real scene or it could be a virtual 3D scene. And many of the devices that can be used to consume this content are widely available now, and newer ones are emerging. If you look on the bottom, I'm showing some of the different sequences, some of the different displays that can be used. So if we start from the far right, we look at the right, we can see light field displays. And those are just emerging. Sony recently had some announcements about that, where actual light is being created that allows the users to view from different positions. Volumetric displays tend to have like multiple layers and discrete positions that a viewer can view from different discrete positions. In the middle, the head-mounted displays are what a VR headset would do, like in a VR game. And then off to the left, we have phones and tablets and laptops and screens. Once you get past the true light field or volumetric displays, if you want to use a 2D display to be showing the scene, whether it's stereo, like in a head-mounted display, or just a single 2D screen, it becomes important to know the position and the orientation of the viewer, so that the scene that gets presented to the viewer on the 2D screen is based on their position and orientation. And in the head-mounted display and the phones, it's based on inertial sensors, and on a laptop or a screen, face tracking or eye tracking can be done to form the estimate of where the person is looking from, so that they can be presented with the proper view. For the MIV standard, I want to talk a little bit first about what the expectation is for the input format. So if you want to use the MIV standard, you need content. You need a representation of this volumetric video scene. And this scene must be captured from multiple cameras, and the cameras are at different positions to get different representations of the scene. And for MIV, there's the expectation that texture and depth are available from each camera. Now, any camera arrangement can be supported, and it could be real cameras or it could be virtual cameras. If you look on the right side here, this particular scene is just showing a layout of cameras. So there's 16 cameras in a 4x4 grid, two-dimensional 4x4 grid. And then on the left, you can see 2 different of the views that have been captured. And on the top is the texture, or just the camera, just the regular color capture from the camera. And the bottom is showing the depth. It's really a disparity. And the way that this disparity works is that brighter is closer. Brighter objects are closer to the camera, and the darker is further away. The MIV working group inside of MPEG and the MPEG iVideo has a variety of content that is used in its tests. And this is just showing illustrations of a few of the different sequences that are used. And along the top is showing the different camera layouts that are being used. On the left, what's called the Intel Frog sequence, there's one-dimensional array, just a whole bunch of cameras in a line. The painter sequence that we just saw in the previous frame as well has this 2D array. The 2 scenes on the far right are both synthetic scenes that were virtually created. And they have interesting camera layouts where they're kind of on the Nokia chest. The third one here is kind of outside looking in. And for a virtual scene, this type of setup is actually reasonable to do because you don't have to worry about the cameras seeing the other cameras. With a real scene, it's a little bit of a challenge in that one camera can see another and you need to do something to remove that. But in a virtual scene such as these, that's not a problem because there's no actual camera there. And so here, these are just some of the used. Here's a couple other scenes, and I want to touch about the whole concept of depth. So depth estimation is not actually standardized. It's not part of the MIV standard itself, but it is necessary. You need to have that depth representation in each of those view positions. The top scene that's shown here is a synthetic scene that was generated. And you can see both the texture, and then you can, on the right side, you can see the depth. Now in this case, the depth is really pretty. It is, it's pretty, it's clean, it's crisp, because it was done virtually. But on the bottom, it was a camera captured scene, and a depth estimation software was run to generate what you see there on the bottom right. And clearly, it has a lot of problems. It's noisy. It's not very pretty. It's noisy, and there's a lot of very visible artifacts. So even though the depth estimation is not part of the actual standard, there's a lot of work that is going on in it, both in the MPEG group and in the actual research community. And there's some efforts that are involving more machine learning and AI. And I'm really hopeful that those will get some better effects because machine learning will be able to realize that the guy's the guy's leg doesn't have a hole in it. And so hopefully we'll start to get better quality. Biggest challenges are temporal coherency, across time in the video, and then spatial correlation, coherency across the cameras. All right, so let's talk about the MIV standard itself. I just wanted to first of all give you a sense of what the inputs are. So the upper left here is showing the MIV encoder side processing. So you have multiple different camera views that have been captured with the depths, and you have the parameters of the cameras themselves. Then you create what are called atlases, and I'll get into that a little bit more on the next slide. But these atlases of both the texture attributes and the geometry are then put through a video encoder. And this is like a standard video coder, whether it's AVC or HEVC or VVC or AV1, any existing video codec standard can be used. It creates a bit stream. And then on the decoder side, we kind of undo this process with the video decoders. And then we have the MIV decoder it has these decoded videos and this metadata substream. And then from that, it creates outputs that go into a renderer that can render the view for the viewers, the position and the orientation. Now in this whole diagram, the only part that's within this red box is within the normative scope that the standard strictly defines. Everything else, implementations have a freedom that they can customize how that they do it. Now, the MPEG-I group still has software that provides to do these steps because it is necessary. We need to study them, and you can't design the standard without having a full working chain. But so for the TMIV has the encoder and the renderer, depth estimation is done separately. So the standard is expected to be completed in 2021. Committee draft was issued just a few months ago in July. So the basic concept of the MIV codec is that you have concepts that are views, patches, and atlases. And that's what I'm attempting to illustrate here. So the left side is showing views. So I have multiple different views here, from different scenes. And then in the middle, I'm showing where patches are formed. So patches are rectangular regions within a view that have been selected by the encoder. And then on the right side, we have atlases, where the patches are arranged inside of an atlas. And then it's the atlases themselves that are what are sent to the encoder, the video encoder. So here I'm going to walk through some of these steps in a little bit more detail now. And again, this is showing what the TMIV software does. And so that's not strictly required that an implementation follows this because encoders have their own choices. But I'm going to walk you through what's being done now in the reference software. So as the input to the sequence, we have the sequence of multiple videos, and we have the camera parameters, and we have texture and depth both. So what the TMIV chooses to do is it selects a subset of the views that it calls basic views. And these are views that will be retained in their entirety. And then other views are considered to be additional views. So the next step that's involved is what's called pruning of the views. So the basic concept behind MIV is that you can reproject views from one view position to another view position, and then try to eliminate the redundancy. So what you're seeing in this case here, where you see the mostly gray with little bits of objects there, is that once you've reprojected one of those basic views to this current view position, and then you subtract, and then you can have what's left, and so you can have less information that you need to represent and decode. And so that allows us to reduce the amount of information we need to send, and hence do compression. And then what you do is you form patches, little rectangular regions from these areas, and then you pack them together into these atlases. And so what's shown here is an example atlas with the texture and the depth. And in this case, the depth is a quarter resolution of the, half in each dimension versus the texture. The MIV standard allows you to choose what resolution you want your depth to be. And then this is what goes into your video encoder, and then you also have your metadata that's sent, and then you undo it at the decoder, and then you can render this viewport based on the viewer's position. So you can track their position, you can render it, and you can reconstruct a viewport based on that position. This is like kind of a walkthrough of what's actually happening on an actual content. So I have some source views, here's my camera layout, and here's a video of the scene that's being shown. And then I can do my MIV encoder, and I can create these atlases. I can have the patches and the atlases. And here's an example of patches and atlases that have been formed. So patches are formed, they're placed into atlases, and then that is encoded. It's sent through the MIV decoder and the renderer, and then based on the user's position, a viewport is generated that walks through the scene. So what's shown here is what we call a pose trace, where there's a predetermined path that is simulating the movement of a viewer through the scene. So the viewer is changing with their 6 degree of freedom, they're changing their position and the orientation. And so in a smooth path, they can change and move. And as they move, the video is rendered for that particular view. And so that is what is actually being shown here on the right. And that's the kind of the expectation of what will be the end. MIV has a number of features and benefits. One of the most important is that it can represent any number of cameras, whether they're real or virtual cameras in any camera arrangement. Now there are level limits on the pixel rate, etc., to constrain the complexity, similar to what exists in a video codec standard. Any projection format can be used, whether it's through traditional perspective camera or an ERP camera. And the camera parameters can be updated to handle moving camera rigs and objects. The encoder can select the size and the number of atlases, patches, and groups. Groups can be used to cluster cameras together to enhance local coherency and substream processing. And the encoders can choose to support fine details better than some other options. So details like hair, smoke, and grass, because you have multiple different camera viewports and views, and then the patches that can be formed, and the encoder can choose how many to retain that detail. And that can also help preserve specularities. Any video codec can be used with the MIV standard. And there's high-level syntax that indicates alignment of atlases with camera views to enable viewport-dependent streaming, substream access for decoding and rendering. Operating modes. MIV has a lot of different operating modes. We talked about the atlases before, where you form these patches and you pack them together. It's also possible to have what's called a MIV view mode, where you have selected a subset of views that you retain in their entirety and you don't form the patches. Another mode we can have is what's called geometry absent, where the depth is no longer required to be signaled, and instead at the decoder side, the depth can be generated. And another mode is called entity mode, where individual objects can be identified and mapped with identifiers to allow different types of use cases. One more option is what's called frame packing, where the texture and the depth and also occupancy, which can be represented as externally, can be packed together inside of one video frame, and then that's sent to the video encoder once, and that enables the use of a single video stream. So this is an So the MIV is based on the V3C, the point cloud coding standard, and it has a lot of similarities. They have a lot of commonality. The MIV references the specification, extends it, it uses patches and atlases, but there are also differences. MIV has more flexible camera arrangements. It has inputs and outputs that are videos and not point clouds, and it has some restrictions to reduce the implementation complexity. But it would be straightforward to support both standards in the same implementation. I'm going to show an immersive player demo. And here's a scene that was captured by 25 cameras in a 5x5 grid. And in the lower left corner, you can see there's a face tracker. So here's me live as I'm moving around. And as I move from left to right and up and down and all around, my position with respect to the scene changes. And hence, what is actually shown on the screen changes. If you look on the lower right, where there's a stack of books and some paint tubes, that's where it's most visible because it's the objects that are closest to the camera. So as I move around from left to right, the relative position of these books and the paint tubes with respect to the background, here's another scene that we can show. And in this case, here's a different scene. And again, as I move from left to right, when it's frozen, you can see the difference. But if I go and I can, in this case, I have a video scene. And so as I'm moving, still the video is playing, and I can still get this effect that I can move around the scene and see different positions as the video plays. If I want to, I can stop it at different positions, and then you can kind of see the motion. So here the man on the left, see how his hand moves around relative to the background, the wallpaper on the background, and his own shirt and face. And then the man on the right, you can see the frog. As I go to a different position, the frog's position starts to block his face, or if I move from a different angle, I can see behind them through the wallpaper. So in conclusion, the MIV standard has been designed for easy deployment. It uses legacy video codecs and GPU rendering and can use current displays for viewing. It supports a wide variety of modes to support a wide range of application, and some technical challenges remain, such as depth estimation and encoding algorithms.